We continue to learn Chapter 4, Linear Transformations. Section 2, Matrix Representation of Linear Transformations. Part 1, Matrix Representation of Linear Transformation L from Rn to Rm using standard basis. We have known that each n-by-n matrix A defines a linear transformation LA from Rn to Rm, where LAx equals A times x. We will also see in this lecture that each linear transformation L from Rn to Rm can be represented in terms of an n-by-n matrix with respect to a basis of Rn. So L of x equals A times x. We first see this theorem 4.2.1. If L is a linear transformation mapping from Rn to Rm, then there is an n-by-n matrix A such that L of x equals Ax for each x in Rn. In fact, the jth column vector of A is given by this way. So the jth column for A just equals L function on the standard coordinate vector. The coordinate vector in the standard basis for j varies from 1, 2 till n. Okay, now we see the proof. If x equals x1 e1 plus x2 e2 plus l plus xn en, then L of x just equals x1 times le1 plus x2 times le2 plus tl plus xn times len. If we denote le1 by a1, le2 by a2, and till len by an, so this formula just equals x1 times a1 plus x2 times a2 plus tl plus xn times an. So this is a linear combination of given n vectors. See, if we have this one, immediately we can write as matrix multiplication. So the matrix A composed by A1, A2 till An as its n columns. Okay, so X is the column vector composed by X1, X2 till Xn as its components. So here A just equals Aij, where A is composed by the n columns here, A1, A2 till An, and each Aj is just Lej. See, it's just Lej, where Lej we can write as A1j, A2j till Amj, m dimensional column vector for each j varies from 1, 2 till n. Okay, the standard basis elements for Rn are E1, E2 till En, and we set the column vectors A1, A2 till An just be L function on E1, L function on E2, and L function on En. Okay, and the n-by-n matrix A is called the standard matrix representation of L because we use a standard basis. There are other matrices that represent L with respect to other bases. So if you use other bases, then the matrix represent L will be another matrix. Okay, let's see this example. Example 1. Ask you to find the matrix representation of the linear transformation L from R3 to R2 defined in this way. So L of x equals x1 plus x2 for the first component and x2 plus x3 for the second component of L of x. Here we don't mention other bases, so we use the standard basis. Because we use the standard basis, so in this case, the matrix A is easy to obtain. So you can just find L of x equals this matrix, see, times the column vector x1, x2, x3. So the matrix A is just the representation of this linear transformation L. So the first row is 1, 1, 0. After you times the vector x, x1, x2, x3, it would be x1 plus x2 for the first component. And the second row times x1, x2, x3 will give you x2 plus x3. Okay. And now we see another example, example 2. Find the matrix representation of the linear transformation L that rotates each vector in R2 by an angle theta in the counterclockwise direction. So given you any vector, if you rotate this vector counterclockwise by an angle theta, then you can first consider L, this function, this operator function on E1. You will get a cosine theta, sin theta, this vector. And the L function also on the second coordinate vector in the standard basis, which equals minus sin theta, cosine theta. Then you write LE1 as the first column of A, LE2 as the second column of A. You will get this matrix A. So the matrix A is just the matrix representation of the linear transformation here. Okay, the figure is like this. Okay, we have the coordinate vector here, the first coordinate vector, the second coordinate vector in the standard basis, and then if you rotate this 1, 0 vector anti-clockwise by angle theta, you will get here this new vector with coordinate cosine theta, sin theta, right? And if you rotate this vector, 0, 1 vector, anti-clockwise by angle theta, you will get this vector. This vector is coordinate is minus sin theta, cosine theta. So the matrix A is determined by these two vectors. Okay. And for an arbitrary vector x, if you do this linear transformation, you just do anti-clockwise by angle theta here, and you'll get here. So this vector is A times x.